Let us continue with the concept of work and energy. Um, let's talk about work of a force using the gravitational force concept. If you remember, we said that the change in potential energy or the change in energy can be described as a force times what could be the change in a force in the distance or the change or the force applied in a change of directions. This concept right here tells you that the change in energy equals a force times a change in direction of that force. So assume there's a particle with mass m, little m, and we want to find the energy of a path given by that particle. So the path is a1 to a2. In this case, could be a gravitational astrophysics or astronautics problem because the distance is an orbit, for example. So we can use the gravitational concept of the forces. In this case, the only thing that changes is the radius because the mass is not changing. Say it's a planet and not a star that is losing mass. So for a simple problem where mass is constant, the only thing changing is the direction. Therefore, the energy can be computed from state 1 to state 2 just by integrating the equation and finding what is the distance in direction at point 1 and the distance and direction at point 2. If you do that, it's very simple because the energy is the change of, is the delta energy, is the energy from state 1 and state 2. So state 2, energy at state 2 minus energy at state 1. And this applies for any problem that you want to compute using the energy approach. So let's go ahead and review our concepts. Looking at this problem or this example where we have a plane, inclined plane, and there's a box sliding down or up, we don't know yet. We want to know if there's work because of the force. So the question is, does the normal force do work from B to A? Okay, so they're telling us that the box is sliding down. And the normal force, as you know, is vertical and this perpendicular to the plane. And the question is, does the normal force do work? And it does not because we are static with respect to this plane, so does not. Next question. Does the weight do work? Yes, that is a different thing. The weight does because the force equals by the mass times gravity, which is the weight, this weight. This makes the component of the force to move down because of the weight. So yes, that in this case, this answer is yes. Yeah, so we're correct. And the work is positive or negative? Oh, we didn't answer this. It's positive because it's um, gaining, is doing work, right? It's doing work. You have to do work to move this box. So continue with the work of a force. Forces which do not do work are basically when they add to zero or they are static. So reactions or frictional surfaces. So when there's no friction, reaction at a roller, weight at center of gravity moves horizontal. So you can capture moments where cases where the force is along the axis and it's not doing any work. But we're getting into more interesting things now that we're talking about principal work of energy. Let's still consider a mass m, little m, and there's a force, capital F. Let's start from the force tangential to an orbit from A1 to A2. So let's capture the force tangential to the orbit is equal to the mass times the acceleration tangential to the orbit, which is the mass times the derivative of velocity with respect to time. If we want to parameterize this equation, we can go to a parameter called S, And doing the chain rule, we do the change in velocity with respect to s, respect to the arc, and the change of the arc with respect to time. Then we have the mass times the velocity and the velocity changing with respect to the arc. Okay, so the force tangential, which is in this case right here given by this vector, times the change or the differential of the arc equals the mass times the velocity times the change in velocity, right? Because just basically what we're doing is F tangential equals mv dv ds. All we're doing is bring the differential to this side of the equation so you can integrate it. Integrating from the point 1 to point 2 and the velocity 1 to velocity 2, we have that at the beginning of the arc, or sorry, at the end of the arc, remember it's always energy at state 2 minus energy at state 1. So it's 1/2 of the mass velocity squared at point 2 minus 1/2 the mass velocity at point 1 squared. And that brings us to the very interesting concept of the changes in energy can be described by the kinetic energy at each point. So now we're not talking about kinematics, we're talking about kinetic energy, which is related to the forces. All right, so the work of a force is equal to the change in the kinetic energy of a particle. This is a concept that you will need to remember, digest, understand. The work of a force, right? So the work of a force is equal to the change in kinetic energy of the particle. All right. Is the energy from state 2 kinetic minus state 1 kinetic. And the units of work are given in Newton meters or joules. And you can see that because mass is in kilograms and velocity squared is mass over second squared. So that gives us kilograms per meter, so meter second squared times meter is newtons per meter or joules. The units of energy is always joules. Force times distance. So in this example right here, this point, this is in newtons, and this is in meters. Now, remember that power is the rate of energy in time. Joules over seconds equals power, watts. So the rate of which work is done. So since U is the change in kinetic energy, the change of energy in time is obviously the change of the direction in time. Okay. So work is joules. Power is watts. So another way to remember is work is force times distance. Power is force times velocity. So work, power. All right, velocity and distance are vectors. Velocity and forces, velocity, forces, and distances are vectors. So force, distance, and velocity, all of them are vectors. But vector times vector dot product vector is a scalar. So this thing is a scalar, and this thing is a scalar. It's just a point of energy. All right, the dimensions are watts, and 1 watt is 1 joules per second. 1 horsepower equals 746 watts right here, or 550 feet-pound per second. So 746 watts. Efficiency is a very important concept. Efficiency is the output work divided by the input work. So like an engine, you put gas and air, well, and oxygen, you do combustion, and then you bring your power out through your shaft, through your transmission. But the engine gets hot, gets warm. So it's not 100% efficient because a change in chemical energy is giving mechanical energy, but there's some losses in heat. So that's why the efficiency is less. You should never get higher efficiency than your initial point. So you cannot get a mechanical thermodynamic system with 120% efficiency because it's just going against the second law of thermodynamics, which is related to entropy, but we're not going to talk about that here. Remember that your efficiency has to be less than 100%. So this number is gonna be a ratio. It's gonna be 0.9, 90%, 0.8, 80%, etc. And the efficiency can be the output work divided by the input work, or using the power output divided by the power input. But it's always output divided by input because the input is larger usually. So let's look at a few problems here. A car weighs 4,000 pounds and is driven down 5-degree incline at a speed of 60 miles per hour. When the brakes are applied, causing a constant total brake force of 1,500 pounds. Determine the distance traveled by the automobile. Yeah, okay, so this is a good problem. If we were to do in the kinematics, it will be pretty complicated because you have to do the acceleration, the time, the distance, the forces. But with the concept of energy, it's just state 1 versus state 2. So the first thing we're going to do is take our miles per hour to meters per second or feet per second. This example is doing it feet per second, which is okay. 60 miles per hour, take it to feet per second using 5280 feet in a mile, and 1 hour is 3600 seconds. So the kinetic energy at point 1 is 1/2 of the mass velocity squared. The mass is 4,000 pounds. You can take that to kilograms if you go to meters per second, but since you're in feet per second, keep it in pounds. So 1/2 of the mass, which is 4,000, the velocity, which is 88 feet per second squared. But remember that this mass is in pounds mass, and they're giving you the mass in pound force. So 4,000 divided by gravity, 32.2 feet per second squared, is going to be your pound mass. Okay, so pound mass is equal to pound force divided by 32.2. And that gives you 481,000 feet pound, foot pound. 481,000 foot pound. That is the state 1. And then state 2 is completely stopping, coming to a rest, so velocity 0. Therefore, this equation turns into 0 because the velocity is 0. All right, so to determine the distance, we can use a simple equation of energy from state 1 to state 2 is negative 1,500. This is the force applied to stop. So force times distance. And then plus the 4,000, which is the mass of the car, or sorry, the force given by the car, but is an angle. It has an angle of 5 degrees. So that normal force is given by sine of 5 degrees. We already know how to do this. So solving that, we can do, this is negative 1,500, this is x, and all this can be computed. Therefore, by computing that, this is times x, and x. The distance is given by the force times distance, okay? But we have to do conservation of the force right here. Negative 1,500 and then this component of 4,000 sine of 5 degrees. Since they're asking for a distance, we have to do the force the body diagram. Then the potential energy is kinetic energy at state 2 minus kinetic energy at state 1. We already have kinetic energy at state 1, and kinetic energy at state 2 is 0. Therefore, all we have to do is solve for the equation where we have 481,000 pounds foot-pound is equal to 11,511 pounds. Oh, it's, yeah, 1,151 pounds times x. Solving for x, you get 418 feet. So the only new thing here is that you set up your energy as your force times distance. We noticed that before. That's why we said energy equals force times the r. R here is x. And if you go back to your diagram, your momentum diagram, you have your normal, your braking force, and your weight. Your weight is going to have this component in the x direction of the plane. So you simply set up negative 1,500 times x, because that's the energy of the equation, plus 4,000 plus x, which is making that distance occur. That is going to give you negative 1,100, sorry, is going to be negative 1,151 pounds times x. Then when you solve for it, you just simply combine the potential energy and the kinetic energy.